Okay, today we're going to do section 2.4, continuity, which is on page 179 in your textbook. The continuity, it just means if a line is or equation is broken or not. If it's not broken, got the wrong marker. If it's not broken, it is then called continuous. So we are at section 2.4, which is on page 179. Is something broken? Well, the continuity is a very important concept, and it is related to limits. What happens is this. For example, to explain what I mean by that, let's look at an example. Okay, there are three conditions for continuity of a certain point. Like, say if you have a function, right? F of x. Now, the function f of x is continuous at a certain point a. We are only looking at one point at a time. So right now there's some point a, x equal to a, where we're trying to figure out if the function is continuous. Well, it is continuous with three conditions. First, f of a has to be defined. If it's undefined, then it's not continuous or anything. Well, that goes without saying, right? But we'll mention that just to be 100% clear. So it has to be defined, of course, which means a has to be in the domain. Number two, the limit as x approach a of f has to exist. Now let's look at an example when the limit doesn't exist to illustrate the point. For example, if you have a broken function, look at example 2.27, where you have a graph that looks something like this. Your function goes like this, like an upside down parabola, and then it stops right here, and then decide to go some other way. Okay, that's your f of x. In example 2.27. Now in that case, I don't know if you can see there, kind of. The point is, when that is broken, when that happens, then the limit doesn't exist, because the limit only exists if the left side limit, which is here, and the right side limit, which is here, are the same. Okay, otherwise you say the limit doesn't exist. Although the left and right side limits exist by themselves, but if they don't equal, the overall limit doesn't exist. So the limit, so the second condition is the limit has to exist. Now, and then for the function to be continuous. Now, and then there's a third condition. Condition 3 says the limit has to exist, and it has to equal to the value of the function itself. For example, if sometimes the limit exists but doesn't equal to the value. Okay, that's the third condition, is the limit has to exist. That's good. Okay, for example, let's look at this particular function. Okay, that's probably x, y equals to 0 or something. That's not a very good picture. Let me draw a better picture. Let's say you have a function that where it's defined at a. Okay, here's a. Here's your function, which is a boring line. So you have a function which is defined at a and everywhere else, but it is defined at a up here for some reason. There's for no reason at all. Okay, yeah, I just want to define it that way. So so the limit exists, right? At a, each side goes to a suitable point. Remember, the limit is only asking you what's the neighbors doing. The neighbors are going this way, right? But at exactly a, I decided to give it a jump. So the limit exists and are equal, right? They're the same. But it doesn't equal to the function at that exact value. And in that case, it's not continuous, still broken. So out of the three conditions, the first condition is not interesting. So the two conditions, for something to be continuous, the limit at that point has to exist, plus has to equal to the function itself. If it doesn't, if the function took off, it's not it's not continuous. It got busted right there. There's a hole right there. If there's a hole, it's not continuous. All right. So continuity of rational functions, polynomials. So at this point, we're just gonna say this, just in case you're wondering. Your regular functions are mostly continuous, such as polynomials. They're theorem 2.8. Polynomials are continuous. And also rational functions, that's polynomials in a fraction form. A rational function might be something like x plus 1 over, I don't know, x squared minus 2. Anything, okay? That's a rational function. These are all continuous. It just means there's nothing broken in there. Except if the denominator is 0, because in a rational function, whenever the denominator goes to 0, then the function goes into an asymptote of some sort, up or down. Doesn't matter. It just, because it's getting close to dividing by 0, so it prepares itself by crawling way up, positive if it's positive, or going way down when it's negative. So then, of course, it's not continuous. I mean, how is that continuous? It's completely busted, right? Because they are going off completely opposite ends. So it's not continuous. But any other spot, like here, that's continuous. As long as it's not dividing by 0, the rational function is perfectly continuous. So a rational function is continuous except for for some spots where if it turns into 0. If sometimes the rational function doesn't ever turn into 0. If that's the case, then it's continuous all over the place. One example of a rational function that doesn't have a denominator, that has a denominator that never goes to 0 would be, for example, x squared plus, if you put plus 2, something like that. X squared plus 2 will never be 0, okay, because you're squaring the x and then you're adding something to it, so it's never going to go to 0. So this thing doesn't have an asymptote. It doesn't crawl up somewhere just because it's a rational function. So all right. So then the next thing we want to discuss the type of discontinuity, which is okay. Let's discuss it slightly. The type of discontinuity is not particularly important, but it doesn't hurt to know it. First is a removable discontinuity. I'll just show it to you on the book. Okay, that one is basically like, where's this anyway? This is we're now on page 184. So the removable discontinuity. The removable discontinuity is just exactly what I just did, right? You have a perfectly good function, you for whatever reason decide to pluck a point out and stick it somewhere else, to make it, you broke it right there, stuck a hole in there. It's discontinuous. It's removable because all you have to make it continuous, just stick that thing back, right? And so so that's just a made-up discontinuity. The next one, this is called a jump discontinuity. See, your function is going somewhere, then you describe it a different way. Okay, one formula goes here, and then for no reason at all, or maybe for some good reason, you decided the next part of the function, your function has a totally different description. So it went somewhere else. So there's a jump, and that's very intelligently called a jump discontinuity. Move on. The next one is more interesting. I mean, slightly more difficult, but still. This thing is called an infinite discontinuity. That means because it's probably a rational function or something similar, like tangent. Okay, the tangent graph will crawl up when tangent is sine over cosine. So when the cosine goes to 0. Because you're dividing by 0. See, the asymptote happened because somebody's trying to divide by 0, so things start crawling towards infinity. Because as you divide by a very small number, you get very, very big, positive or negative. So that's the infinite discontinuity. You just have to have a mind for that. Realize there's such a thing, and then we'll move on. Next, let's see. All right. So then let's look at some examples. Okay. Now next, we are now on at example 2.30, which is on page, what is that? 185. Okay, let's look at. Now we're at page 185. And look at example 2.30, which says that it wants you to look at some discontinuity of a rational function. Okay, f of x equal to, let me write this down, x squared minus 4 divided by x minus 2. Now, what kind of discontinuity is that? Well, at first sight, this is a rational function, right? So it's probably that infinite discontinuity where the stuff cross up the asymptotes. I'm talking about, yeah. Anyway, however, in this case, however, it's a trick because you notice that's x squared minus 4, which has x minus 2 as a factor, which means that this, you can cancel x minus 2 out of it. And this function is defined only when x is not equal to 2, right? Because if x equal to 2, then you divide by 0, so that's not acceptable. So then, but then if you cancel out the x minus 2, see, the x squared minus 4, difference of squares. Never forget the difference of squares. So that turn into the plus and minus version. And then cancel out by x minus 2. And then, so that's just x plus 2. So this function, while it looks like a rational function, it actually is only x plus 2, which is just a line. Okay, but it's a line with a hole in it because it's not defined at x equal to 2, and so it's discontinuous at it. Well, it's not even defined. So so it's that first type that we saw earlier. Is this thing, okay? There is basically some line x plus 2 with 1 point plucked out of it because they stuck this thing on the bottom, which forces x to not be 2, but otherwise it's identical. Okay, it's only different when x is 2, right? Can you see that? Anyway, that's good enough for anybody. Next, move on. Next. Okay, now we next problem you have. I'm looking at example 2.31. I'll just talk about it. It's one of those functions, you have two of them, and they want you to say, well, yeah, show is discontinuous. That's probably because you have two formulas, so it's like the previous case where one formula goes this way and the next formula goes off somewhere else, so you have a jump. So there's and so that's why it's discontinuous. And things like this can be discontinuous, but unless you line it up properly, you have two functions, you can arrange it, move it down and up or something until the 2 points connect, then it is continuous, even if you have two functions. I mean, like something like this. You have one function doing this, and then the next function might do that. But as long as the 2 points are connected, you're good. Anyway, so right. So next, let's look at another rational function. Now this time, you can't cancel it out. So page, well, at the same page still, example 2. So we'll look at example 2.32. So this time you have a simple rational function, f of x equals to x plus 2 over x plus 1. Okay, whatever this thing is, you know that this thing, however it looks like, it's going to crawl to infinity, both directions, at -1, right? So let's see if your book draw it out. Nope, they are too lazy to draw it out. Fine, whatever. I was hoping they draw it out so that I don't have to. But you can, you know that that's going to happen. So it's going to go to infinity or negative infinity, depends on which side you approach, at -1. X equal to -1 is going to be broken. So that it has a infinite discontinuity there. All right, but being that your book is too lazy to draw a picture, I'm not going to draw it either. Let's move along. Next. Okay. All right. Now there's the next thing just says if your function has a continuity from one side only, like okay, like this thing, right? This is continuous from it's okay on one side, just broke right here, but it was fine before. Or on the other side, same story. It's okay on the other side. Let's see, let's move it closer, make sure you can see it. Move it from the other side, which is fine, until it's broke. So then you call it is continuous from the left or continuous from the right or something like that. All right, which is fine. And then okay, let me erase the board. So example 2.33 we're looking at, which is on page 186, which says that we have a rational function. It wants you to figure out when is this thing continuous. Okay, so well, it's probably continuous wherever it's defined because it's just a rational function, but we're going to do it anyway. So so you have f of x equal to x minus 1, that's called x squared plus 2x. Okay, here's your rational function, and where is it continuous? Well, you know that it's continuous except the denominator is 0, where it will crawl up the asymptotes and go to infinity. So first you figure out when is the denominator equal to 0. So to figure out that, so you need to calculate, okay, calculate x squared plus 2x equal to 0, which means you factor this out, that means x equal to 0 or x equal to -2. So on those 2 points, it crosses to infinity, and then I'll draw the line here. Oops. I'll just draw the number line here. So you have, so on the number line, okay, you have 0, x equal to 0, and x equal to -2. Those are the 2 points that there's this thing is gonna go nuts, right? The rest of the time is perfectly good. So so you can use the beautiful Desmos calculator and plot this thing out, which your book decided not to do, but I typed it into the Desmos calculator, and let's see, where is it? Well, I just need to find it. Yeah, watch me now. I can't even find it. Let's not even care. The point is, so it's continuous anywhere that's not -2 or 0, which is how your book puts it. Another way of saying that it's continuous everywhere except -2 and 0 is you use the set notation. The set notation says it is continuous from -infinity all the way up to -2, and then that just means and, right? Is the union, which is and then -2 to 0, and the last part from 0 to infinity. That's the union. That's the set notation. You notice you have to use parentheses, not brackets. Okay, that's important because brackets means you include the number 2, and you can't include it. Like we said, the -2 is not acceptable, and it goes to infinity. So the parentheses means 2 is not included, whereas the bracket, if you were to write this, that means 2 is included in the set notation. All right. So move along. Example 2.34. continuity over an interval. Example 2.34 wants you to look at this thing, 3, 4, which is a square root situation. Okay, you have your function is f. Okay, f of x equals to the root of 4 minus x squared. All right. What is that thing? Well, it's a square root and x is being minused, which means there's only a limited number of things that can be x, because when x gets too big, you'll be taking the square root of a negative number, which isn't defined for the square root function. So it's quite limited. Where is it limited on? Well, when is this thing 0? Is 0 when x is 4 minus something is 0? Well, 4. Take the square root of 2. So when x equal to 2 or negative 2 plus or minus, so then this thing will become 0. If x is less than that in absolute value, that is, if x is 1 or if x is half or something, this thing is okay. So the graph of this thing is x is limited between 2 and minus 2. Otherwise, this thing doesn't exist. So the function is actually half a circle. Is defined from minus 2 to 2, inclusive of both ends. It's okay if x is plus or minus 2. It can't be an inch bigger or smaller. Okay, it's defined here and nothing else. So the function is defined or continuous. In our case, we're talking about continuous. So, well, it's continuous, and you can see that it's continuous. But it's basically at your point at this stage, anything that's defined is continuous where it's defined. So the answer, where is this thing continuous, is going from minus 2 to 2 with with brackets. Brackets means the endpoints are included, everything in between plus the endpoints, whereas parentheses means everything in between, endpoints not included. So anyway, next. Yeah, the composite function theorem just means if you have two functions and it's continuous and the limit exists, then the composite, when you put it together, it also exists. That's yeah. Having said that, let's move on, because at this point you don't need to know exactly why that is. It's just kind of obvious. As an example, let's look at example 2.35. Okay, you have, they call this a composite sine function. So you have two functions in 2.35. That's on page something. Where's the page? 187. All right, this is on page 187. So you have two functions in here. It doesn't even tell you that, but the point is you have two functions, f of x equal to x minus pi over 2, and then g of x equals to cosine x. So then what is f of g of x? Then that gets you the whole thing where this is talking about. Then the composite, the g of f of x then equals to cosine. You plug that in there, so it equals to cosine of x minus pi over half. So when that happens, then if you need to calculate some kind of a limit, such as in this example, they want you to calculate the limit as x goes to pi over 2, cosine of this stuff, then yeah, so that is just that you can just calculate the limit in here first, okay, and then calculate the result in cosine and come up with some answer as you would imagine. that's what theorem 2.9, the composite function theorem, is about. It's just stating something that's intuitively what you would have done anyway. So that's cosine, that would be equal to cosine of 0, which is 1. Okay, now next, moving along. The next section, we are not going to talk that much about it. Your book feels like proving that sine function, the sine and cosine is continuous. We'll just say that it is because, well, the book never proved that y equal to x is continuous. You know, the original x. How do you know x is continuous? The function f of x equal to x. We said from the very beginning that this is continuous, but the book never proved it because, well, it's obvious, ain't it? Well, so is sine, cosine. So we'll skip that for now, and I'll do that later as a project at the end the end of this class. So so moving on along the intermediate value theorem. The intermediate value theorem is something that shows you where the continuity can come in handy. That is, the intermediate value theorem says that if you have a function, okay, that you can prove that it has two values. Say you have a function, and it is sometimes here at one point, earlier point is here, and then later point it got to a different spot over there. Then at some point the function, if you pick a value in between, right, like a river, it used to be here and then it got over there. Then if you have a river somewhere in between this thing, then your function must cross the river at some point. It didn't somehow get around and not get there. That's what the intermediate value says, assuming your function is continuous. If your function isn't even continuous, then you can just go somewhere, jump, and got over there and never had to cross the river. But assuming your function is continuous, the intermediate value theorem says if you went from one side of the river to another side of a river, you have to have crossed the river at one point. That is the whole sum of the intermediate value theorem. All right. Where's my camera?